So the alternating series test. Okay, so first, what is an alternating series? So an alternating series is a series whose terms alternate from positive to negative. Okay. So just alternate plus, minus, and so on. Okay. So for example, this series here, sum n equals 0 to infinity, let's say -1 to the power of n times 1 over n. That's an alternating series. Another example, sum n equals 0 to infinity. Let's do cos of n pi over n squared. Okay, so these are alternating series. Let's see why. Okay, if you plug in, no, so let's start at 1 here, by the way. Can start at 0, both of them, because I'm dividing by n. Okay, so let's start them at 1. So if I plug in 1 here, I get -1 power 1 is -1. So my first term here is -1. Then if n is 2, -1 power 2, it becomes positive 1/2, so plus a half. Then if n is 3, this becomes odd again, so it's negative. So it's -1/3, plus a quarter, and so on. Okay? So you see it's an alternating series, minus, plus, plus. It alternates, plus and minus. Questions? Okay. This one here.
Wait, I have a question.
Yeah.
So any odd denominator, just going to be a minus in front?
In this case.
In this case? Okay.
Yeah, if it was n plus 1 on the bottom, then it will be the opposite.
Okay.
Okay. If n is 1 here, so cos of n pi, so cos of pi. So you know cos of pi is -1. So this will be -1 over 1. Then if n is 2, cos of 2 pi is +1 over 2 squared, which is 4. Then if n is 3, cos of 3 pi is -1 over 9, and plus 1 over 16, and so on and so on. That's my series. Okay, easy. That's it. That's the definition of an alternating series, plus, minus, so on. Okay. So now the question is, how am I going to determine whether such a series converges or diverges? Okay. So there's an extra element here. It's the alternating term. Okay. There's an alternating term, and the rest is a regular term, just like we did before. Okay. So here's the test. I'm going to write it sort of like a flow chart, okay, like a tree of decision that you're going to use to decide whether your series is converging or diverging, okay? So here's what you will do. So I'm going to write this series like this. Okay, so this is going to be the test. So let's -1 power n or cos of n pi, whatever, an alternating term times a positive term. Okay, just like we have here, -1 power n times an, which is 1 over n. Or here, cos of n pi, which is just like -1 over n power n, times 1 over n2, which is an. Okay. the first thing you will do, okay, when you see such a series, is you will use the divergence test. Okay, so you will right away, you will go like this. You will ask yourself the following question: what is the limit as n approaches infinity of an? Okay, just the term, what's the limit? So if it is not 0, or if it is 0, let's ask yourself, is the limit n approaches infinity of an, is it 0 or not? If it's not 0, well, we know our divergence test tells us that the series diverges. Good? And as you know, in the divergence test, if it is equal to 0, then the test fails. I don't know whether it converges or not. Well, in the alternating series, that's very good. If it is 0, the series converges. It's even easier. Okay, so what I'm saying is very, very big, very good. Is that you look at the series like this, you disregard the alternating part, you take the term that is positive, and you do the limit of this term. If it is 0, the series converges. If it is not 0, the series diverges. Easy enough? Doesn't get easier than that. Okay, so an alternating series, the only thing you have to do is take the term and evaluate the limit. That's it, and check if it's 0 or not. Questions?
What term?
What? Sorry?
What term do we use? Because like here you used an, but what would that be like? Let's just say an example.
In this case here, this would be an. Okay, in this case here, this would be an. So 1 over n2. It's everything besides for the alternating term. The minus 1 power n, put aside. Okay, we're good?
Yes, sir.
And yeah.
In another case, how would we identify the an?
You'll see. It's basically the absolute value of this term. Okay, so the minus 1 power n could only be 1 or minus 1. So disregard this. The cos of n pi could only be 1 or minus 1. Disregard this. Okay, it'll be clear. You'll have it one of these forms. That's all you'll have. Okay? Okay. We're not done. Okay, we're not done. So now I established whether my series converges or diverges. Very easy. Now, if it converges, I need to be a bit more specific. Okay? So there's 2 types of convergence. And this is what I'm going to do now. Okay, I'm going to do another branch in my decision, okay, in my tree. What I'm going to test now is I'm going to take the series an, the series without the alternating term, the series itself. Okay, I'm going to consider this series. Imagine I had the series without the minus 1 power n. So this series could converge or diverge. Okay, if it diverges something, if it converges something else. Okay, so if it converges, okay, if it diverges, if the series without the minus 1 diverges, so it converges only when there's an alternating term. If you take out the alternating term, it diverges, then we say that the series negative 1 power n an converges, right? Still converges, but it's called conditionally. Okay, it converges conditionally on the on only condition is if you keep the alternating term here. If you take out the alternating term, you get a divergent series. Okay, we'll do examples in a minute. But if it converges even if you take out the alternating term, then we say that the series AN converges. This is called absolutely. Example, sum n equals 1 to infinity negative 1 power n times n over n2 minus 1. So let's start this at 2.
We do the limit of 1 over n2 minus 1. We don't include the n in there, right?
Of course you do. Of course you include the n.
Oh, we do?
Yeah, this is an, the whole term that doesn't alternate.
But I thought we said that the numerator was not included.
Who said that? I didn't say that. I didn't say the numerator is not included. I said the alternating term is not included.
Oh, okay, yeah, I see.
Okay. So now limit as n approaches infinity of the term, n over n2 minus 1. This is infinity over infinity. Let's do L'Hopital's rule. Limit n approaches infinity, 1 over 2n. This is 0.
Sir,
Yep.
shouldn't it start at 1?
Why should it start at 1?
Should we make it start at 1 though?
No.
Or okay.
No, you don't have to make it start at 1. The only ones that we insist on making it start at 0 are the geometric series, because then you could use the formula, or else you have to make an adapt, right? You have to adapt. So.
Oh, okay.
So the other ones you can start wherever, it doesn't matter. Anyways, what's important to determine whether a series converges or diverges is the end terms at the end when they become very small. That's what's important for me. Okay. First terms, it's finite, it's nothing. Okay. So this is, of course, I have to make sure that I don't get a problem. Like if it's 1, then I get 1 over 0, and that doesn't work. Okay. Okay, so I took the limit of an, I got 0, so I'm in this situation here, right here. Okay, so it converges. So I know that the series negative 1 to the n over n2 minus 1 converges.
Sir?
Yep.
I'm sorry, I wasn't paying attention. How
Okay,
did you get
well,
1 over 2n?
I did
the
L'Hopital's
second-
rule. I did L'Hopital's rule.
Oh, okay.
Right?
Okay.
The derivative, yeah?
Okay.
Okay. Anybody else? Questions? Okay. So now we established that it converges. Now we have to determine whether it converges conditionally or absolutely. So what do? I'm going to test the series. I'm going to focus on this series, 2 to infinity of without the alternating term. And I'm going to see what happens to this series. Is it converging or diverging? What do you think?
Diverges
Very good. Why?
because it behaves like 1 over n, which is a
Very
harmonic
nice.
series.
Very nice, very nice. Okay, so you have two choices. So I know that it's going to diverge exactly for the reason that she said. It's because it behaves like 1 over n, and so now I have two tests that I could use, either the comparison or the limit comparison, whatever you prefer. What do you prefer? Let me know what you prefer. I'll do it.
If limit comparison always works, we should use that one.
Okay, let's do limit comparison test. So limit as n approaches infinity of an, so n over n2 minus 1 over bn, which I'm comparing it to 1 over n. Okay, so I'm just going to write here an bn. You get limit as n approaches infinity of n2 over n2 minus 1. And if you do L'Hopital's rule, you will get 1, okay? And that is greater than 0, right? My limit comparison test tells me that if I have a divergent series and when I divide, I get bigger than 0, then an diverges as well, okay? So, and the series 1 over n diverges because it's the harmonic. Okay, so always specify, right? Justify harmonic series. Then the series 2 to infinity, n over n2 minus 1 diverges as well because of the limit comparison test. Okay, so again, the series an here, I just showed that when I divide it by bn, limit at infinity, an over bn, I get 1, which is bigger than 0, and the series that's on the bottom that I compared it to diverges because it's a harmonic series. Therefore, my series, the an series, diverges as well by the limit comparison test. So what do we show here? Let's go back to my general idea here, is that I just proved that the series n equals 2 to infinity of n, oh, sorry, the alternating one. Minus 1 power n times n over n2 minus 1. So what does it do? Converge or diverge?
It converges
Converges what?
conditionally.
Very nice. I'm going to put it pink here, conditionally. And I'm done. That's how it works. So 2 more tests remaining, the ratio test and the root test. I'm going to put them both at once because they're pretty similar. And we're done all the tests, okay? So the ratio test is as follows. It will take the limit as n approaches infinity of n plus 1 over an in absolute value. Okay, so the n plus 1th term divided by the nth term, you'll do this division, this ratio, and you will find a limit at infinity. And there's 3 possibilities for this value. If this number is greater than 1, if it's equal to 1, or if it's less than 1. So if it's bigger than 1, then the series an diverges. If it's smaller than 1, the series an converges. Okay, and if it's equal to 1, then the test fails. You have to go to another test. Okay. This is the ratio test. It's a good test. I like it, and you're going to use it a lot for power series, as you will see. Oh, I forgot a V in converges, by the way. Converges. Okay. Let me write down the root test, which is very similar. You will do now the limits. Again, we'll do examples as n approaches infinity, and now you will do the nth root. So it's called the root test. The nth root of the absolute value of an. And same idea. If this root is greater than 1, equal to 1, less than 1. Okay, so if it's bigger than 1, the series an converges. Smaller than 1, diverges. Converges. And if it's equal to 1, again, the test fails. Okay. So the series n equals 1 to infinity. So let's do negative 9 power n over 4 power 2n plus 1 times n plus 1. Okay, so here's the series. I want to know if it converges or diverges. Okay, so you look at this, and I don't know what to do. If there wasn't this n plus 1 here, then this would look pretty much like a geometric series. Okay, I could probably organize it into a geometric series. But there's an n. Okay, so it won't be a r power n. I have the r power n, I could fix it here, but there's an n. So I need something else, okay? Integration, I don't think you could integrate this, it's crazy. If you do the divergence test, the limit at infinity of this, it's definitely gonna go to 0. Comparison, I don't know what I should compare it to. Oh, maybe comparison, oh, no, because there's an alternating. No, so let's try the ratio test, okay? So anytime you have exponentials, the ratio test is a very good candidate, okay?
Sir,
So, yeah.
on top, is it a 9?
Yeah, it's a 9. I know my 9s are not very nice.
Okay.
Let me fix my 9 in a second. It's better, I think. Okay, so let's do limits as n approaches infinity of the absolute value, big absolute value of, so an plus 1. So this is an, right? So I'm going to plug in an plus 1. So every n becomes an n plus 1. Negative 9 power n plus 1 over, and now replace the n by n plus 1. So 4 to the power of 2 times n plus 1 plus 1. So it's n plus 3 times, and here I have n plus 1 is n plus 2. And on the bottom, I have an, so which is just negative 9 power n over 4 power 2n plus 1 times n plus 1. This is the limit that I need to evaluate. Good?
Sir, could you explain how you got +3?
Plus 3 here.
Yeah.
Yeah, plug in n plus 1 here. You get 2 times n, so it's 2 times n plus 1 plus 1.
Okay.
Okay.
Thank you.
So here we have limits, n approaches infinity. So let's just put everything on one fraction. right? You remember when you divide a fraction by another one, you just flip the bottom one and you times. Okay, so that's something that you should know from high school. Okay, so again, a fraction divided by a fraction is the top fraction times the bottom fraction flipped. So let's go. -9 to the power of n plus 1. So it's just -9 power n times -9, right? That's -9 to the n plus 1. Over 4 power 2n plus 3. So 4 power 2n times 4 power 3 times n plus 2. Is that okay with everybody? This is my top term. And then I'm going to times it by my bottom term flipped. So I'm going to flip this one. So this denominator will appear on top here. So times 4 power 2n times 4, right? 4 power 2n plus 1 times n plus 1. And on the bottom, -9 power n. That's what I have. Any questions on this limit? Okay, so it's cleanup time. Okay, this is the fun part. -9 power n, -9 power n is out. 4 power 2n and 4 power 2n is out. Equals limit n approaches infinity, absolute value. So on the top here, I have -9 times 4 over 4 cubed. So a 4 could cancel. So you have -9 here and 16 on the bottom times, and here I have n plus 1 over n plus 2. Questions? Extract the number out of the limit. Okay, so it comes out, but he takes his absolute value with him, so it becomes plus 9 over 16. Limit n approaches infinity of the absolute value of n plus 1 over n plus 2. The n's are positive. I don't need the absolute value anymore. This limit using L'Hopital's rule gives you 1. And so I have my answer is 9 over 16, which is less than 1. So I just showed that my an plus 1 over an, the limit is less than 1. So done. The series n equals 1 to infinity, -9 power n over 4 power 2n plus 1 times n plus 1 converges because of the ratio test.